Welcome back to an Introduction to Real Analysis. We continue now with Chapter 4, Section 3, Taylor's Theorem. Let's talk about derivatives of higher orders. Remember that when a function defined on an interval I has a derivative, we notate it as f prime and consider that as a new function. What if that function, the derivative, itself is differentiable? Well, then we would call f prime the first derivative and the derivative of that the second derivative of the function f. If the second derivative has a derivative, we would call its derivative the third derivative, and so forth. If you can take n different derivatives of a function, if it can be differentiated n times, we would say it is an n times differentiable function. Now note, beyond the third derivative, this prime notation becomes a little unpleasant. Instead, if you want to talk about higher derivatives than the second or third, you use this notation. For the nth derivative, you put f to the n, and specifically, that n is in parentheses. This is not to be confused with the nth power of f. If you just put f to the n with no parentheses, most mathematicians would understand that as the nth power. Inside parentheses is our sort of convention for that many derivatives. Now, the mean value theorem stated that if you have a continuous function on a closed interval differentiable on the open interval, then there is some point on the interior where the derivative at the interior point is equal to the average rate of change, f of b minus f of a over b minus a. Or if you rearrange some terms, f of b is equal to f of a plus f prime at some interior point times the distance b minus a. Now, if you somehow happened to know some bounds on f prime, an upper bound of capital M and a lower bound of little m, what would follow is that f of b is in between f of a plus little m or big M times b minus a. In other words, the value of f of b can be approximated to a certain extent if you can control how big f prime is. Let's take a look at an example. Let's approximate the value of root 10. F of x equals root x is continuous and differentiable on the interval from 9 to 10. We've chosen 10 as an endpoint because we want to approximate f of 10, root 10. 9 as an endpoint is because f of 9, or root 9, equals 3 is not an approximation at all. We know that quite exactly. So by the mean value theorem, f of 10 is equal to f of 9 plus the derivative at an unknown point in between 9 and 10 times the distance 10 minus 9. Plugging in the fact that 10 minus 9 is 1 and f of 9 is 3, and f prime is given by a nice explicit 1 over 2 root c, we see that the square root of 10 is equal to 3 plus 1 over 2 times the square root of c. Also, c is in between 9 and 10. So we have the following result, that root 10 can be explicitly written as 3 plus 1 over 2 root c. The only trouble is c is an unknown point, but it is between 9 and 10. So certainly, if c is between 9 and 10, its square root is in between 3 and 4. Therefore, 3 plus 1 over 2 root c can be approximated by 3 plus an eighth and 3 plus a sixth. So root 10 is somewhere in between 3 plus 1/8 and 3 plus 1/6. Now, here are 3 plus an eighth and 3 plus a sixth, with the square root of 10 to 3 decimal points written in between. And that's not a terrible estimate for pretty little work involving the square root function. 3.12 to 3.17, and the square root of 10 is 3.16. We got a pretty decent estimate without having to try very hard. So let's move on to Taylor's theorem. Taylor's theorem generalizes that previous approach. If you know higher derivatives of a function on an interval, and you also know precisely what the value of these derivatives is at one endpoint, this will give you a very good estimate of f of b at the other endpoint. It tells us, up to a small error, any n times differentiable function may be approximated near a specific point, specifically by a polynomial. Now, why is that a good approximation? If x is near to x naught, in other words, if x minus x naught is fairly small, once you start raising it to high powers, that will be very, very small. So you are adjusting the value of your polynomial by increasingly smaller amounts as long as the degree of that polynomial, this exponent n, is larger and larger. So first, let's define what a Taylor polynomial is. Suppose you have a function which is n times differentiable and defined near a point x0. The nth order Taylor polynomial at the point x0 is given by p for polynomial, sub n for what order, superscript x0 for where you are basing this polynomial, it's a function of x, is a sum going from 0 to n. As your index goes, what are your terms that you're adding up? The kth derivative evaluated at x0. Note, if k is 0, the 0th derivative is understood to just be the original function f, divided by k factorial times the distance x minus x0 to the k. So here's Taylor's theorem. Suppose you have a function that has n continuous derivatives on the interval from a to b. Also, the next derivative, the n plus first derivative, exists, but is not required to be continuous. Then for any pair of points, x and x0 in the interval from a to b, there is a c in between so that the value of f of x is given by the Taylor polynomial of order n, based at x0, of x, plus this extra term. It involves the n plus first derivative at the unknown point c, divided by n plus 1 factorial times x minus x0 to the n plus 1. Compared to the definition of the Taylor polynomial, this term only differs in the fact that this point where you are evaluating the next derivative is unknown, but it is between x and x0. And we can, right? So let's prove it. Now that term, this hanger-on that's being added to the Taylor polynomial, we're going to call it r sub n superscript x0 of x. We're calling it the remainder term. Now, if you have seen other presentations of Taylor's theorem, we're using what is called the Lagrange form of the remainder. Other presentations are all completely equivalent. The notation changes a little bit. Don't worry about it. This is what we're calling the remainder. The thing that is added to the Taylor polynomial in our desired statement of Taylor's theorem. Observe, c is where this next derivative is being computed, but it simply is a point that exists between x and x0. So if you change x0 or you change x, presumably c also changes. Now let's suppose that f of x0, f prime of x0, all the way through the nth derivative of x0 can be computed exactly. In other words, in the Taylor polynomial, everything is quite explicit and computable. Then, this Taylor polynomial is a nice specific value that you are not estimating, but you know precisely. If you can then put bounds on the n plus first derivative at an unknown point, then everything else here is nice and computable, so you can put bounds on f of x. All right, that said, let's get on to the proof. For notation, let's define m sub x x0 to be the following quotient, f of x minus the Taylor polynomial at x, divided by x minus x0 to the n plus 1. In the claim of Taylor's theorem, f of x minus the Taylor polynomial divided by x minus x0 to the n plus 1 is hopefully equal to the n plus first derivative at an unknown point divided by n plus 1 factorial, but we don't know that yet. What we do, however, know is that by rearranging terms, multiplying this over here and adding the Taylor polynomial, f of x is equal to the Taylor polynomial at x plus this new quantity capital M times x minus x0 to the n plus 1. Remember that x is not actually varying. We picked an x0 and we picked an x. So x is not really a variable in the sense that we're going to let it move around. Think of it as a fixed value. Now let's let g of s be this new function. S is now a variable. F of s minus the Taylor polynomial at s minus this fixed quantity, okay, x and x0 are not changing, times s minus x0 to the n plus 1. Okay, so here is an expression that we derived for f of x. Here is what we have defined g of s to be. We now claim that for all k from 0 to n, if you take k derivatives of the Taylor polynomial, then evaluate that derivative at x0, you reclaim the kth derivative of f evaluated at x0. Okay. Now, if you take k derivatives of any of the terms in the polynomial where you have a constant times x minus x0 to a power less than k, if this power is less than the number of derivatives you take, well, you will differentiate it away to 0. However, suppose you have an m which is bigger than k. if you only take k derivatives, you are left with an x minus x naught to a positive power if m is larger than k. Substituting in x naught, this will then be 0. So when you take k derivatives of this Taylor polynomial and evaluate it at x naught, the Taylor polynomial is made up of a bunch of these terms. This is just a constant, and here's the only place where x shows up. So taking k derivatives of terms of small power will differentiate away to 0. Of large power, we'll still have some sort of expression like this, which will evaluate to 0. The only term where that doesn't apply is the kth derivative of the kth term. Now, when you take exactly k derivatives of this specific term, you'll multiply out a k, then you'll multiply a k minus 1, then a k minus 2, all the way down to a times 1. You'll exactly cancel out the k factorial. What will be left behind is x minus x naught to the 0 power. Ignore it, that's just 1. So all you get is the kth derivative of f evaluated at x naught. So the kth derivative of the Taylor polynomial evaluated at x naught recovers exactly the kth derivative of f evaluated at x naught. So we derived this expression for f, we defined this function g, and then we showed this relationship between the kth derivative of the Taylor polynomial and the kth derivative of the function f. Let's start computing derivatives of g. Note, derivatives of g will be derivatives of f minus derivatives of the Taylor polynomial. The variable of g is s, so this is a constant, so we will quite easily take derivatives of this expression here as well. And recall that the 0th derivative of a function is simply the function you started with. So for all k between 0 and n, you'll end up with the kth derivative of f minus the kth derivative of the Taylor polynomial, minus, now this is just a constant. If you take k derivatives from 0 to n, since you started with more than n powers, you'll have this product, n plus 1 times n minus 1, all the way down to this right here, times this constant, x naught minus x naught to the n minus k plus 1, once you evaluate this derivative at x naught. So we already know that the kth derivative of the Taylor polynomial at x naught will exactly equal the kth derivative of f at x naught. Plugging in x naught here gives us a 0. So overall, we get a 0. So the kth derivative of g at x naught is 0, and that holds for all k from 0 to n, including both 0 and n. So here was something we derived for f, our definition of g, and we happen to know that all derivatives of g at x naught are 0, at least the 0th derivative, aka the original function, up to the nth derivative. However, g of x, if you simply plug in s equals x, gives this expression right here. But that's exactly 0 thanks to this equality that we derived for f evaluated at x. So g of x is equal to 0, but g of x naught was equal to 0. So by the mean value theorem, there is a point, and let's call it x1, somewhere in between where the first derivative of g is 0. But now, the first derivative of g at this unknown point is 0, but the first derivative at x naught was also 0. So by the mean value theorem, there is a point in between x naught and x1 where g double prime is 0. But now, g double prime at this new point is 0, g double prime at x naught is known to be 0. So by the mean value theorem, there's an x3 somewhere in between where the third derivative is 0. Continue on in this way until you find something, x sub n plus 1, which we're going to call c, somewhere in between x naught and n. Now remember, x1 was between x and x naught. x2 was between x naught and x1, therefore also between x naught and x, and so forth. So this new point we found is somewhere between x naught and x. What is true about this point that we've renamed c? The n plus first derivative of g evaluated at this point must be 0. So here was f and g, and we know there is some point in between x and x naught where the n plus first derivative of g must be 0. However, p sub n is an nth degree polynomial. So if I take n plus 1 derivatives, it vanishes completely. So taking n plus 1 derivatives of g will kill this term Exactly. The n plus first derivative here, since this is exactly an n plus first power of our variable s, we'll exactly end up with an n plus 1 factorial times whatever this constant was. Recall that the definition of m sub x x naught was this quotient right here. So now, since we know g, n plus first derivative evaluated at c, is 0, we end up with an n plus first derivative of f evaluated at c. This vanished, and this has a nice explicit formulation, and over here we have a 0 as well. So 0 is equal to the n plus first derivative of f evaluated at c minus this quantity right here. Okay, we're basically there. We found a c in between x and x naught where the following quantity must be 0. You can rearrange this to get Taylor's theorem. Okay, first move this term to the other side, multiply by this, divide by this, then you add the Taylor polynomial over, and you end up with exactly this statement here. So we have finally proved Taylor's theorem. Now in the proof of Taylor's theorem, we found that the nth Taylor polynomial is the polynomial which satisfies p of x naught is f of x naught, but p prime at x naught is f prime at x naught, all the way down to the nth derivative. So it's a polynomial that matches the behavior of f from evaluation up to nth derivative evaluation at the specific point x naught. This is why the Taylor polynomial is a good approximation to f. Not only do we match the value of the function at x naught, but we match how fast the function is changing and how fast the derivative is changing, and so forth and so forth. So intuitively, if x is very close to x naught, since I now have a polynomial that has the value of f, but also how fast it's changing and how fast the derivative is changing and how fast that's changing and so forth, we should be remaining very close in value to f. So one could ask, if the Taylor polynomial should, in strong quotes there, I mean, it's math, it should do whatever it does. But if the Taylor polynomial we expect to approximate f better and better as n gets larger, what will happen if we let n just go to infinity? Now, if all derivatives of the function exist, you can define a Taylor series for a function centered at x naught. And you simply continue the Taylor polynomial out to infinite degree. Now, there's no guarantee this series converges anywhere. Even if it does converge, it's not necessarily converging to the function f of x. We hope it is. We hope that the Taylor polynomials provide better and better approximations to the function f. So they should converge and they should converge to f, but that is something that you have to prove. So for example, consider 1 over 1 minus x, centered at 0. One may quickly prove inductively that the kth derivative is given by this expression right here, k factorial times 1 minus x to the minus k minus 1. So if you evaluate this at 0, you end up with a 1 to a power. So the kth derivative of f at 0 is simply k factorial. Now if you construct the Taylor series, those factorials cancel out. You had a kth derivative divided by k factorial. They go away, now you just have x minus 0 to the kth power. But that's the geometric series, which does in fact converge to 1 over 1 minus x, but not everywhere, only on the interval from minus 1 to 1 and not including the endpoints. This function f of x, however, its domain includes negative 1, and it includes lots of stuff beyond the interval from minus 1 to 1. So this Taylor series does converge to the function f of x, but only on a piece of its domain. Here's another example, f of x equals e to the x. Again, we're going to center everything at 0. What's nice, since e to the x is its own derivative, is that we can take as many derivatives as we want. Plugging in x equals 0 to any derivative yields a 1. So the Taylor series is quickly constructed as 1 over k factorial times x to the k. It is not difficult to show this converges for every x. So we'd like to show that this Taylor series is actually equal to the function we started with. We have shown that this Taylor series converges everywhere, but is it converging to e to the x? Well, take an arbitrary positive value of x. According to Taylor's theorem, the value of the function at x is equal to the nth order Taylor polynomial evaluated at x plus a remainder term. Here is the next derivative evaluated at an unknown c times x to the n plus 1 over n plus 1 factorial. Now, since c is somewhere in between 0 and x, as n goes to infinity, this remainder term converges to 0. So since this is converging to 0 as n goes to infinity, this Taylor series is converging to this constant e to the x. Now, functions that have Taylor series that don't just converge, but converge to the function you started with, at least on an interval around where you're centering everything, are called analytic. These are functions that locally, in other words, near x0, can be approximated to arbitrary precision by Taylor polynomials. So we've seen that 1 over 1 minus x is analytic. But not every function is. There's an exercise coming up in chapter 5 that is specifically to build a function that has a Taylor series, and the Taylor series converges, but it does not converge to the function you started with. Think back to the definition of a derivative. If the derivative exists, then think of it as the slope of a tangent line, the slope of a line that best approximates the value of the function. So the derivative existing can be thought of as the function can be approximated very well by a line. And a line is something that has at least one derivative. So we mentioned in passing there's a sort of converse to Taylor's theorem that sounds very similar. We're not going to state it formally, we're not going to prove it. However, if a function can be approximated in a very particular way by a polynomial of degree d, then it must have d derivatives. Taylor's theorem also gives us a quick proof of something called the second derivative test. Now, a strict relative minimum of f at a point, what we mean is that for all x's in an interval around c other than c, f of c is definitely less than f of x. This is a strict relative minimum at a certain point c. A strict relative maximum, of course, defined similarly. Now, continuity of the second derivative is not necessary for this statement, but the proof is more difficult. It's left as an exercise. The proof of the second derivative test also generalizes to nth derivative tests. That's also left as an exercise. So here's the second derivative test as we're going to state and prove it. Suppose f has two derivatives, and let's assume the second derivative is continuous on an interval ab. Let x0 be somewhere on the interior so that the first derivative is 0. If the second derivative is positive at x0, then x0 is a local min. If the second derivative is negative, then x0 is a local max. Okay, let's prove. We're just going to do the proof of f double prime at x0 being positive. Since the second derivative is positive and we have assumed that the second derivative is continuous, then there has to be an interval around x0 on which the second derivative is positive. Flip back to exercise 3.2.11 to see how this is proved. Now, by proposition 4.2.8, since f double prime is positive on an interval, f prime is strictly increasing on this interval. Now, since f prime is strictly increasing on this interval and it was equal to 0 at x0, it had to have been negative to the left and positive to the right. Therefore, we already know that since the derivative went from negative to 0 to positive, we had to be at a local minimum. So we're really just putting together a bunch of stuff we've already done. Note, we did assume f double prime is continuous. It significantly simplifies the approach here. As mentioned earlier, there's an exercise where you prove the same thing without this assumption. So let's go over this section. Taylor's theorem is really a generalization of the mean value theorem. Think of the mean value theorem as Taylor's theorem for first degree polynomials. Taylor's theorem can also be used to show that Taylor series that converge have to be converging to a desired function. Specifically, isolate the so-called remainder term and show that it converges to 0. If you also know that the Taylor series is converging, then you will have shown that it is converging to the function you started with.